echo out of my computer, but now it's good. Okay. Hello, everyone. Welcome again to Rocq N'Roll. We're going to try to speak into the microphone. My name is Roger.
I'm Claire. We're both PhD students at Penn.
That's right. And a while ago, we came up with this sort of unusual idea to hear proofs. But before we hear proofs, we're going to listen to something. Is that the table of sounds? All right, that was fun and not expected. Welcome again to Rocq N'Roll. We're going to first talk about the conception of this tool. We're going to talk about how we applied proof and music theory to build the thing that we wanted, and how we used the language server protocol as well as the MIDI protocol to make this a little easier on ourselves, and then some of the creative design choices we made in hearing our proof. Let's start.
First off, in case anyone here isn't familiar with Rocq, it's a dependently typed language. It's a proof assistant. All of us love using it. I love Rocq so much that we both love it so much that we were wondering what would this sound like? What would this feel like? Because even though we relate with it by coding and whatnot, can we get more of a body feel with Rocq?
Exactly. And this was motivated by a couple of questions. So the first question.
Right. What does the proof sound like? What does sorry sound like?
What do different tactics sound like? The Rocq often loop that we do when we're writing proofs is we write something and then we type check it interactively, and it's sort of a conversation between the programmer and the type checker. What does that conversation actually sound like?
And so just like how when you hear something that clearly sounds terrible, like can we get that too from proofs? If you write a proof that you've been able to QED, like does that sound correct too? So yeah.
Yeah, or does a bad proof sound dissonant? Also, what does sound better even mean? Does it even mean anything for music to sound good? We'll talk a little bit about this.
And finally, sometimes I'm lazy and I'll use auto and I'll have no idea why my goals are gone. And so I was wondering, like, under the hood, what is happening with auto? And maybe can we hear that?
So we have a couple ideas to answer these questions. One, what is this conversation like? Well, hearing the sort of tactic response loop that the programmer writes is kind of interesting and can give us a few insights. And it's also just kind of fun. I think it makes Rocq a lot more bearable when you get fun sounds coming out of your proof. And fundamentally, this tool is about fun, right? This is an art tool. We have some practical elements that we'll talk about and some maybe things that can give you insights, but primarily this was just to have a good time. Two, yeah. What does it mean for something to sound better? Well, if you want to ask someone what music that sounds good is defined as, or how to define that, first you'd have to define music, and good luck with that. So we decided to use a little bit of dissonance as an indicator of errors, but of course dissonance isn't a bad thing, and it doesn't mean that music sounds better or worse. We're just using it as a heuristic. And finally, this is the one aspect in which we think our tool is somewhat practical. And when you write a Rocq proof, for those who aren't familiar, you're trying to solve some proof goal of a mathematical proof. And you might do this very, very exactly with a number of very explicit steps that are easy to read. But Rocq also provides some automated reasoning, so it can provide a bunch of these and throw a bunch of them at once at a goal and just solve it for you. And this is really helpful when you have a paper deadline. But when you try to understand your proof, this is not as easy to reason about. You might not know what's actually going on. You can actually break this apart and deautomate it, right? You can print out the individual things, but what these actually are is not always easy to understand. But to understand how much lifting a certain automated tactic is doing, it's actually sometimes easier to hear a complex sound and hear a sequence of notes or a chord rather than look at all these tactics and see which ones are actually being applied. For our proof theory.
Right. So first off, you'll think like, how would this sound like? How would we parse it? So we decided to approach it by tactics. So in a rock proof, you'll use tactics, which are like, think of it as functions like intros, like intro these variables I want to prove, or apply this existing lemma I want to use. So literally, you can look up what tactics are, but intros, apply, etc. Yeah. And then, so there's not only tactics, but there's also like automated tactics like auto, e-auto. And then there are also things where you can program, you can like do, you can write code about your tactics, like using semicolon or tacticals like uh, retry, yeah, try. And so we started out with a fixed map of tactics. So there's a lot of them, and we map them to these pitch and velocity MIDI pairs. So first they have like a fixed set of notes, but then given like any kind of proof, like we can parse any given rock file, the sound of the fixed notes will change given the state of the proof.
Exactly. So to summarize, we have a bunch of tactics in Rocq that are well known, and we map those to different sounds using something called MIDI. This is sort of what a proof looks like, turning individual tactics or lists of tactics into music. How does music theory play into this? Well, we wanted to make things sound interesting and a little bit weird and fun, but not too weird so that you couldn't hear kind of the either consonant elements or complexity elements of an individual tactic. Of course, it's really easy to do consonants with chromaticism. This just means you put things in a scale where basically any two or more notes will sound good together. But we actually decided to abandon this and just let it sound really weird and interesting. Do we really want consonants? The answer ended up being we don't really care. But how do our tactics actually work? Well, auto is a tactic that does lots of things. Maybe it does one thing, maybe it does 20, maybe it does two. And it does these in sequence, right, over a tactic, or if it's applied to many things, over many tactics. So the idea of auto playing many things as an audio sequence, or sort of an arpeggio, which is a chord where you play all the things individually, auto can kind of take a solo in our thing. You know, auto might play two notes, or again, it might play 20. And to jam with your proof when your proof is playing more than one note, but is actually playing this sequence of notes, auto gets kind of fun. With semicolon, this is applying many tactics to many sub-goals at once. So if you have a proof that you need to prove some property, and to prove that you need to prove three sub-properties, semicolon can apply a tactic to all three of them at once. And simultaneity makes us, I think of chords or simultaneous chords, right? Many notes at the same time. Finally, tacticals, which are higher order tactics, which take in a Rocq tactic and produce something else. So maybe try this tactic, but don't worry if it doesn't succeed, or do this tactic again and again until you can't go anymore. These should probably augment the notes that the tactics already make. So we stay with the bass note, but we're going to raise it by an octave or bend it or do something interesting there. The architecture of this is relatively straightforward. We parse a .v file, that's a Rocq file, into our Rocq N'Roll program. We have a conversation with the LSP, the language server protocol. In our case, we chose to use VSCock, and that's how we get the notes for the MIDI and also the visual design for the GUI, which we'll be showing off tonight at the performance.
So the language server protocol is a way to universally programmatically interface with programming languages. Sounds all tautological, but basically when you use like an IDE and you have features like autocomplete, or you can search through a complex code base, and you might be using this for a variety of languages, all of that is being communicated using the language server protocol. So in order to parse our Rocq proofs and actually do something given the proof state, we used one of the Rocq LSPs. We actually tried both. Coq LSP and VS Cocktop. And we actually ended up using VS Cocktop. So that's the LSP behind the VS Code extension. And then really there's like a bunch of endpoints in general if you want to use this for any language, but we mainly relied on proof view. So if any of you use VS Cocktop on VS Code, it's when you step through your proof and then like right side panel shows up and it shows you the state of your proof and what subgoals you have. And then really, honestly, this is really basic. This did a lot of the heavy lifting work on figuring out what to do given the proof state. And all we had to do was like parse the JSON output. Oh, and we use JSON RPC messages to send requests and take parser responses. And then sometimes if there was a lot to parse, we made use of Claude code. So it's very good at just parsing JSON responses. And then finally, so we mentioned like tactics like auto, where under the hood, you have no idea what's happening. So already you can, at the top of your Rocq group, oh, sorry, oh, my bad. At the top of your Rocq, like this, is this good? Okay. So at the top of your Rocq proof file, you can do set info auto or set info e auto. And then when you get to the auto tactic itself, you'll see on the proof view, like the actual tactics under the hood. So there's a lot of stuff sometimes that can happen. I wasn't even aware of it. And so we take that. So that could actually be multiple different tactics. And then we parse it and send it to MIDI. So yeah, really like, if you want to parse any kind of proof, I think, not even just using Rocq, just like use a language server, use the language's language server, and then you'll get info.
Yeah, the language server was really powerful and can give you a lot of information. Coq LSP gave us less information that was easier to parse. VS Coq Top gives you everything, but it's a nightmare to parse. So it's kind of simple versus everything everywhere all at once. And how much information do you want to get out of your language server? How much do you actually need? We ended up just pulling more and more and more until we upgraded language server protocols because we realized that we wanted to make things really complex and interesting based on the proof state, and we had to use an upgrade. As far as MIDI, so MIDI is the musical instrument digital interface. This is basically how electronic instruments talk to each other. This is used basically globally in electronic instruments. The spec is very standard. And it's a way for us to send little binary packets to a synthesizer, right, an electronic instrument, and get sound out of it. So we generate MIDI in our code base. Rust ended up being better than OCaml for this. We wanted to do this in OCaml. For those who are not familiar, the Rocq language is implemented in the programming language OCaml. So we wanted to stay relatively native. But it turned out OCaml was actually pretty bad for MIDI generation. So we ended up using Rust, and we're a lot happier with that. Ideally, in the future, we would actually want to generate MIDI directly out of the language server itself, like out of the VS Coq extension, or even out of the Rocq prover. This is a future direction for Rocq N'Roll 2. For our synthesizer setup, we're using the Teenage Engineering Op1 field, which is a really nice piece of hardware that you can get a lot of fun sounds with, and you'll hear us improvise on that during the performance. GarageBand was surprisingly good for this, though. When we were getting things set up, we used GarageBand as our synthesizer and had a really good time. For now, things are very simple. We're keeping the MIDI single channel and manual ADSR. If you know what those mean, you'll know what this means. If you don't, you can just understand that we're not messing with many of the audio things. But the key point is that we're using MIDI, and that makes us synth agnostic. So this really is a plug-and-play tool. We'll put up a QR at the end. If you have a synthesizer of your own and you'd like to hear what your proofs sound like in that synthesizer, it will work. Finally, the rest of this project, once you've done the LSP and MIDI, is open design space. And we got to play a lot within this space. Because this is an art project too, we had a bit of room for fun. So we didn't initially have a GUI. We just used kind of a text-based thing and ended up writing a GUI, which was a good amount of fun and I think makes the performance much more engaging. We also have an autoplay feature. So if you have a nice long proof and you just want to jam it out in the background, you can just hit go and play it on a track. Listen to it while going to work. And finally, we've tried to make our code base relatively modular and debuggable, so please do PR us and extend it as you wish. So that's it, right? We're done. That's kind of the end of the tool, or maybe not. There are kind of open proofs or open questions. We've talked a lot about dissonance. What is the value of dissonance in a bad proof, in a proof that gives up, or a proof that fails or doesn't type check? It's very funny, right? But maybe is dissonance something that could be appreciated instead of rejected in this tool? Can dissonance tell us anything that the type checker can't? What's on the table for Rocq N'Roll 2? We talked a bit about this, maybe going direct in the language server protocol. We want to do some things with multi-threading so we can get more complex MIDI and chords. And finally, this is an art project ultimately. And how much of this do we want to turn into a science project, right? Do we want this to be a practical tool where hearing your proof actually tells you some unique information outside of the type checker? Or do we really just want to jam out to our proofs? Right now, we're just going to jam. We're going to play during the performance, and you might learn something about your proof. You might understand that this auto is really doing a lot of heavy lifting more than that one. But for now, we're here to have fun. With that, thank you for coming. Please feel free to scan our QR and PR. We're at time for questions. Right, yes. I'm going to stop.
So as you mentioned, we are. I'm Phil Father from Edinburgh.
Hi.
Well,
That was also very cool. You talked a lot about, does this kind of proof for bad proof respond sound this way? You have a couple of examples you could run so that we could see it, a nice proof and a
Yes,
proof?
for time, we're not going to do that now, but I will be happy to show you offline. I know, yes, we do.
We are listening to a concert like this.
Yes.
Yeah, we're
so during the
playing
performance,
tonight.
Here are some good proofs and specs.
yes. Please do come. Yeah.
Jeffrey Young, Epic Games. This isn't really a question, it's more a suggestion, but I'd be interested to know what the concert C compiler sounds like.
Oh yeah. So we will play a longer example of a sophisticated and well-known rock proof. It's not from Concert, but you may recognize it. And Concert is probably for Rocq N'Roll too. So catch you next year.
I'm interested in
Yeah.
going through some old papers that you had used Rocq to prove things and hearing like, oh, well, all the Stephanie lyrics work is like hardcore.
Yes. What's their musical style, you know?
Is plastic.
Yes. We actually have enjoyed doing this just a little bit, right? As we're tightening up the tool. Now it's like sort of time to play and have fun. And playing different proofs has been really interesting, right? Some things don't sound as musically interesting because it's like 30 module imports. You call one command and your proof is done, right? But if you're building things from first principles, you very often get this iterative, expansive music performance really for yourself. It's a really good question, right? And then of course that differentiation is going to depend a lot on the prover's style. Yeah, Harry.
Harry Goldston, so I've done some work on automatic deautomation.
Yeah. We looked at your paper.
Sonic relationship between the automated and the automated versions and like, do you know, like, what would that sound?
Absolutely. So great question. We looked, so for Harry's paper with Jessica Shee, Benjamin Pierce, and Andrew. Okay, yeah. Is about deautomating rock proofs. So you take these proofs that have automated tactics and you turn them into lists of longer, sort of more atomic tactics. And this is, would you like to answer this or should I keep going? Just want to give you floor time or air time. But,
oh, okay, yeah. So like for this is more of like a live coding tool where it just like parses the proof, and then we personally like we just pick like the fixed notes to the tactics. So I would say I don't think there's a relationship between like I don't think you would be able to see that relationship, right? 'Cause, I mean, we like is he asking like does auto sound similar to how we break it down?
Yes. So I think the way you break this down in the tool is you kind of get everything auto is doing, and then you just insert that back into the proof instead. Yeah.
Oh, okay.
So great question. No, it's okay. We'll answer quickly, which is that yes. So auto sounds like all the things that it is playing. So theoretically, yes, right? Auto at least does. And then semicolon is there's a certain amount of like how many goals is semicolon being applied to that is a future direction right now, because that actually turns out to be much harder with just the language server protocol. Really, if you wanted to make this easy, you would just fork the Rocq prover and do it in Rocq. But then you have to make OCaml MIDI, and you also have to fork and build the Rocq prover. So this is why it's a future direction.
All right, I think I solved our tech issue for the next talk. So we will once again thank the speakers. Thank you for rocking around.